is 100 Newton. And then there's a beam like that. Beam like that. So this one will deflect not?
Yes.
Yes. Can deflect like that. So can we find the deflection like that not?
Then.
Yes. This is simple Macaulay. Or we have something like that. And then the built in there. And then this deflect there. So this deflection there called delta or y. Can we find this one in Macaulay not?
Can.
Yes. So let us do that simple one. Cut here. What do we have there? Cut do we have there? We have a P there. So we have an X here, right?
Yes.
We have a moment here, right?
Yes.
My moment is equal to PX, right?
Yes.
So we have a deflection like that. We know the boundary condition there. The deflection here, we have the value. We have a value, we have a value. And here, deflection is 0, right?
Yes.
And also, your y is 0. Your y dot is also 0. The slope here is also 0, right?
Yes.
So x is equal to 0. X is equal to, let's say, 2 there. 2 meter here. X is equal to the slope dy dx. Y dot is equal to dy dx, right?
Yes.
So, this is the formula. So, we put in Macaulay. Remember the Macaulay? What's the Macaulay? What's the Macaulay method? EI D dan 2y dx square is equal to moment, right?
Yes.
This is the Macaulay method there. So, we have y and x. This is your x here. Up and down is y, right?
Yes.
Yes. So put there. What do we have there? EI dy dx equal to moment. My moment is equal to px, right? Right, me?
Yes.
We integrate here. What do we have? We get EI dy dx equal to px square over 2 plus constant, correct?
Yes, correct.
Yeah, and then we integrate some more, we have EI y there. So y is the deflection, up and down there. X right, x is to left and right. Y is up and down. We have y there. So what we have? Px cubed over 3 times 2 is 6 plus ax plus b. Are you with me now? We got a deflection formula here.
Yes.
Okay? Put EI at the bottom here, 1 over EI. So we got a deflection formula, right?
Yes.
And then the same thing here. Put EI back here. We got a slope formula here, right?
Yes.
And then, but we have A and B. We have to solve for A and B first, right?
So yes.
So what is A and B? I know the slope here is 0, right? I know the
Yes.
deflection here is 0, right?
Yes. Boundary condition.
So put the deflection here is 0 and x equal to 2. 2 here, we got A not?
Can get, yes.
Yes. And then we got A there, and then put the deflection here 0. Deflection here is 0. X equal to 2 there, and A, you know. And then you got a B not?
Yes, can.
Okay. So those are the basic simple integration. Simple integration to find the deflection. That is from Macaulay. From Macaulay. Because you integration into x. You integration px into dx. So this become x square over 2, right?
Yes.
You integration into dx. Those are simple method of integration. You can find the slope and deflection. For here, we got a slope x0, y0. Let's go. We got deflection x0, y0. Got x equal to 2, y is also 0. Use that boundary condition to find A and B. No problem, that one. Now, look at this. That Macaulay system, there's a simple integration. Now, I put the one during the buckling. This is happening. Before buckling, the diagram is like that. Are you with me?
Yes.
During the buckling, this is the diagram. So before the buckling, sigma P over A only, right?
Yeah, betul. Yes.
Yes. Here, how do you calculate the sigma there? So they have a distance here. We can find the y there. So how do I calculate that one? So if I draw that one, very big like that, not very nice. Yeah? Put a load there. So that must be a load PP. This is also a moment there, correct?
Yes.
This is what we have to realize. If not, this one is not, it's not static, right? This must have a moment inside that one to make it static, right?
Yes.
So what do we do into this? What do we do into this? So I put an equation back. What is the moment then? My moment here is equal to P times Y, right?
Yes.
If I put a load like that, P times X. But when buckling is happen, there's a deflation there. The load times the deflation create a moment there. And the moment there, this moment here will create stress not.
Yes, will.
Same thing like when we have a moment like that. So we have a stress here. Sigma is equal to M, Y over I. This is your Y, right? This is your Y. Then there's a stress tensile here. This is positive stress. This is negative stress, right? My over I. So there's a moment here, and zero at the middle, right?
Yes.
Stress, positive, stress, negative there. So this concept here, we require to know the deflection. Are you with me?
Yes.
So this is the formula. So in your that one data sheet, that Y maximum, that one is being given in your data sheet, correct? Are you with me?
Yes. Why is wrong?
The deflection. The deflection is given in your data sheet. Are you with me?
Yes.
We can always use it to find the stress. What is the stress again? Stress is, see that? Go back to the basic formula there. If things like that, we have a P and then we have a moment there. How do you get a stress there? We got a moment, we got P there. So stress at B. So stress at A is equal to what? Must be P over A, compression, negative, right? And then we have a minus My over I, correct?
Yes.
Negative P over A and then negative My over I there, because the moment is like that. But what is sigma and B there on the left? Negative P over A plus My over I, correct?
Yes.
So this is just go back to basic stress and strain. Basic stress analysis again. But only the formula to find that deflation, that one, we have to go through in detail. Let's look for example. Okay? How to get that? This is not moment time X. This is moment time Y now. Remember that?
Yes, P times Y.
P time Y. It's not moment P time X anymore. Now, how do we do that? Yeah? We have the equation EI d square Y dx squared equal to moment. My moment is not px now. My moment is py now. Are you with me?
Yes.
And because this is the other way, sign convention up and down, this will minus py. If you write down inside, we have ei d square y dx plus py is equal to 0. Can we write that one?
Yes, good.
This is when the integration become complex. We learn this in mathematics, differential equation, right?
Yes.
How do we do that one? We assume, because there is a solution in mathematics, one of the solution in differential equation, what did it say? If we have something like that, dy dx, and then plus alpha square y is equal to 0. When we have something like that, the solution is y. The solution is y a sine alpha x plus b cosine alpha x. This is the proposed solution. Not necessarily correct yet, because this is a curve, sine cosine curve. Are you with me?
Yes.
So this is the proposed solution. Not necessarily true yet. So this is mathematics. So how do we brought this into mathematics? Mathematics formula is something like that. Something times y, that constant, that one, call it alpha square. So sine alpha is there, and then cos alpha is there. The solution. Remember that? What is the y? Y is the deflection. Are you with me?
Yes. Yes.
The solution for y, x to that one, y up and down that one. So y is the deflection. That's the proposed solution. So how do we make this one same like that? This is what engineering play around with mathematics. So we put that one must leave dy dx. What do we have here? dy dx square, put down there, plus p over ei times y equal to 0, right?
Yes.
So I want to make it like that. So this one, p divided by ei must equal to alpha, correct?
Yes,
Must
correct.
equal to alpha square, correct?
Yes, correct.
Alpha square. This is interesting. Then just put it aside there. P times ei, that one is equal to alpha square. P over ei is equal to alpha square. Then we follow this formula. Now this one become dy x square plus alpha y square equal to 0. Is it same not? Same not?
Yes, it's the same.
No. When it's the same, now we put back the solution. The solution is being given by the Euler. This is how the Euler come. The mathematician Euler proposed this solution. This solution is that the y is a sine alpha x plus b cosine alpha x. Remember that? This is your x, and there's deflection there. Your x equal to 0, x equal to L, x equal to L. The length is L there. Correct me?
Yes.
Put a P there, put a P there. This is how the deflection. You can find the Y anywhere there. Anywhere X, you can find the Y. But to satisfy this, we have to do the boundary condition. The boundary condition at X is equal to 0, Y is equal to 0, right? Here. X is equal to 0, your deflection is 0, right?
Yes.
So put it there. What do we have? Y is 0, 0 is equal to A sine X is 0. X times alpha,
0.
0. Sine 0 plus B cosine 0. Are you with me?
Yes.
What do we have there? A sine 0 is 0, right?
Yes.
0 times A is
0.
0, 0, 0. And then B cos 0 is what?
Cos 0, 1.
1. So this formula to confirm that your B value is 0. Are you with me?
Yes.
Your B value is
0.
0. So when this one, my new formula become what? My new formula, this is 0. My new formula become A sine alpha x. Right?
Yes.
Formula for that deflection y there, anywhere at x there. And then x is equal to L. X is equal to L. My y is equal to 0 also, right?
Yes.
So what do we have there? 0 is equal to A sine x is L, alpha L. Right?
Yes.
So this must be 0. We have two entity there. Sine something and A. So to make that one 0, which one is 0?
Sign something.
Yes. Not the A. If A is 0, there's no equation there. Are you with me?
Yes.
To validate this, sine alpha L must be 0. So to validate this, A cannot be 0. If the A is 0, there's no equation there. So sine alpha L must be 0. Are you with me?
Yes.
Now we understand. When the sine something is equal to 0, that angle is equal to what?
0 and 180.
0 degrees and then 180 degrees, right?
Yes.
And then what was the other?
360 though. Nothing.
Yeah. So we got this one. This is in radian. This is equal to 0. And then we have here is pi. And then we do another 2 pi. Then 3 pi. Correct?
Yes.
Yeah. For the 0 case here, we cannot solve anything. Are you with me?
Yes.
So we take the first pi there, 180 degree pi there. So that inside here must equal to pi. Inside here must equal to pi to satisfy become 0. So what do we write there? What do we write there? Here, alpha L must equal to pi, correct?
Yes.
Alpha L must equal to pi. So if I square this one, square this one, square this one, square this one, what do we have here? Alpha square, L square is equal to pi square, right?
Yes.
And then we go back. What is alpha square? Alpha square is equal to P over EI, right?
Yes.
So what do we have there? P over EI, L square is equal to pi, right?
Pi square.
Pi square. And then what is the P there? P is equal to pi square EI over L square and times 1 there. Times 1, right?
Yes.
So what is this?
Euler.
This is the first Euler when pin equal to pin. Your beta is equal to 1. So this is how the Euler formula is being derived. Using the simple integration of indeterminate case. Indeterminate case, you have to propose a solution. Are you with me, guys?
Yes.
So because in undergraduate, when you put a load there, you just take this distance here. This distance is before the load. In postgraduate, when you put the load there, it's already bending, right? See that?
Yes.
This is the real free body diagram, not the before bending. But you learn this in when? Yeah, when you do your master's class. So for undergraduate, this is more than enough. The moment is equal to P times that distance, whatever it is, before the deflection. But in postgraduate, we have to draw the deflection after it's being loaded. The stress must be calculated after it's being loaded, not before it's being loaded. Are you with me, guys?
Yes, doctor.
So more accurate. So that's one. If you're interested to do your postgraduate later on, so we'll go into that. So the same thing with this. How do we calculate the stress when the buckling already happened? Yeah? When the buckling already happened, how do we calculate the stress there? So must be the moment and the P. We must know the deflection there. Why? So the P time Y, you got a moment. The moment time, so we got a stress. For before deflation, just the diagram become like that. Straight one, there's no moment there. If we include the moment, the things become like that. So how do we understand this one? Stress here and here must be stress P over A and then stress due to moment. Sigma due to P over A and the other one is sigma due to My over I. Correct? Here and here. One is
Yes, correct.
positive, one is negative. So go back to the basic understanding of that. So when you are given the Y, that one, can we find the stress there? Yes. Are you with me, guys?
Yes.
I don't want to go to detail how we derive that one, that formula, okay? The Y one. This one of the example how to derive that one. Clear?
Clear.
So again, remember that Y is what? That Y is that deflection. X is equal to what? For this case, L over 2, put it there, and then you got the value there. And then P times Y, you got the moment, and then moment My over I again, we got the stress. Because this is stress is below the yield, remember that?
Yes.
So below the yield, so there must be stress there, not just P over A. Not just P over A, because it's already bended by the buckling. There must be a moment there. Okay, there's another topic. There's another topic. Call it eccentric loading. Put it here. So we have the formula when it start to buckle, right?
Yes.
Because beta is equal to 1 over 4, right?
Yes.
But look carefully here. What if slightly there? There's slightly load there. E, you call it E there. Distance E, very small. Let's say 10 mm, 10 cm only. Even if we put a cross section like that, that load is not in the middle there. The load is, let's say here. You got the distance not? What happened when this is happening? This one automatically bending, right?
Yes.
This one is automatically bending. It's not about buckling. Are you with me?
Yes.
For this case, the centric loading that one, if you draw the free body diagram, the top there, cut it there, what do we have there? Got a P there, E there. What do we have there? You got a P, we got a moment, right?
Yes.
So this is automatically bending because from the beginning there is already moment, right?
Yes.
The same thing with this. So we have a case of buckling, look like buckling, but the load is not in the middle. There's a E, they call it distant eccentric, the one. Let's say like that. And then we got a distant there, a distant P there. And then I got a distant P there. So this will automatically bending, right? From the beginning.
Yes.
We don't have to calculate the buckling load there. From the beginning, there must be bending, right?
Then we still call it as buckling.
Because we want to use the formula Y in that one.
Oh, okay.
This is not buckling, this is bending. Just like this one. When we have something like that, put a load there, what happened there? This one got bending, not here. Got moment here.
Got
Yes, when this moment bengkok like that, right?
Yes.
So this inside that one here already got moment through that one, right? So the same thing like this. This is a moment case. But can we calculate the stress there? Yes. Can you find the Y there? Yes. That's what in the formula call it. Why the deflection there? Call it Y. In your textbook, that one, they call it secant, right?
Second formula.
That's the distance, that one.
V
Can you read it for me? Why the formula, that one?
V max equals to E.
V max, I call V Y, that one. That means for V max is Y. Okay? Why is that?
E big bracket. Then secant square root
Secant square root what?
P over EI.
P over EI
Then out of square root
out of square root
KL over 2.
AL
K
KL
over 2. Then bracket minus 1.
minus 1.
Mm.
Okay, whatever it is, those value can be calculated not?
Then
So, and then you got the Y there. Deflection. When you got the deflection there, this is when the E is the eccentric distance here. Are you with me, guys?
yes.
So all of these are numbers, and times the E, we got the Y there. So we just use the formula to find the stress. What is the stress there? Stress must be what here? First must be P over A, and then the other one must be plus minus MY over I, right? So that one, the V is inside here. P times Y. P times E plus Y plus V. Are you with me?
Yes.
P times distance. What is the distance from here to here? What is the distance there? E plus V, right? E plus V. Are you with me?
Yes.
When you know the V there, you can calculate the moment there. The moment is P times that distance. So that distance can be calculated from the formula. So the original distance is E there, and then deflection is that much, the V. And that one proposed by V. So the other one use Y, whatever, same thing. Okay? And then you got that one, you got the moment. You got the moment, you got the stress not? Yes. Are you with me, guys?
Yes.
So this is more complex, but this is just a syllabus for the masters, just for you to get the grasp. What is we are talking about? Okay, guys?
Okay, then we just use the formula lah.
Yes, yeah. For the distance, just use the formula. You don't have to derive it.
Okay.
Okay?
Okay.
So you understand the whole system there. There is a Euler formula, there is a Rankine formula. Both are the same. Okay? Just giving the load only. And the other one is the deflection one. When thing is deflected, how do we calculate the stress? We have to know the Y, that one, or V, that one. So that is also given to you. When there is eccentric, when the load is not exactly in the middle, there must be eccentric. Automatic, that one will be bent, right?
Yes.
So that is bending case already. Not really buckling, but we use the buckling formula to find the deflection there. Because this is also sine cosine equation. Are you with me?
Yes.
So that's all about it's not that much actually about there. So we cover the whole process, that one. Okay, I think we stop today. Okay, I think we got good luck. We have class tomorrow, and then we review the whole thing tomorrow. Okay.
Okay.
Okay. Thank you very much. Good luck. Okay. Assalamualaikum.
Thank you so much, Doctor.
Thank you, Doctor.
Thank you.
Thank you,
Thank you, Doctor.
Thank you, Doctor.